In this section, we're going to move on to some areas that you probably not seen before. Areas of some special kinds of polygons. So to begin, I have drawn 3 regular polygons, and regular polygons fit perfectly inside a circle, so that each vertex of the polygon is also on the circle. And you'll notice that I have labeled the center of each circle, and that is also the center of each polygon. It's a nice little convenient fact. I've drawn in the radius of each, and I've also drawn this length called A. And that little A stands for apothem. The apothem is a special distance that regular polygons have, and it's the distance from the center of that polygon to the middle of one of its sides. The number of apothems every regular polygon has is equal to the number of sides that it has. So for example, in this triangle here, this is an equilateral triangle. I've drawn in 1 apothem, like so. There's also one here and also one here. With the square, there's one here, here, and also here. And with this regular pentagon, there's an apothem here, 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 and also here. And an apothem is going to be a necessary component of what we're going to do in a little bit. Again, notice that when I draw in the apothem, this entire length gets cut into 2 equal pieces, 2 equal pieces, 2 equal pieces. And should probably also clarify that since these are 3 different polygons, those are 3 different lengths. Also, this radius drawn from the center to this vertex bisects the angle. Because this is an equilateral triangle, we know that every angle is 60 degrees. So we know that each of these angles are 30. With a square, we know that each of these angles is 45. And with a regular pentagon, we know that the angles add up to 540. We have a formula to determine that from chapter 8, if you need a refresher. Use that formula on a 5-sided figure, then divide that answer by 5 to find the value of each individual angle, which comes out to be 108 degrees. So when we bisect that, each of these angles is 54. And that's going to be important a little later as well. So now that we have this thing called an apothem, let's put it to work. And I'll start one at a time. So here I have that same circle, same equilateral triangle. I have this value that I called S. This is not a 5. This is S for side length. And I drew in 1 apothem. Also notice that I drew in all 3 radii. Every regular polygon has the same number of radii as it does sides. So an equilateral triangle has 3 radii. There are 3 segments I can draw from the center of the polygon to each vertex. And by doing so, I have split this triangle into 3 smaller triangles. One I've colored in blue, one I've colored in purple, and the other one I've left blank so we can see what's going on inside of it. We have 3 sides, and we turn that into 3 smaller triangles. We know the area of one triangle is 1/2 base times height. In this case, our base is the length S, and our height is the apothem. So I will rewrite that as SA. And then I will need to multiply that by 3, since we have 3 equal triangles. Because this is a regular polygon, we are guaranteed that all 3 of these triangles are congruent. They all have the same radius. They all have the same apothem. The apothem is the height of each triangle. We know that this length is equal to this length is equal to this length because all the sides are the same. That's part of the definition of a regular polygon. So I have 1/2 SA times 3. And we are going somewhere with this, so we'll come back to this shortly. We're going to try to establish a pattern of things here. Moving on to the square. And yes, we know how to find the area of a square, but for the purposes of establishing a pattern, let's look at it from a regular polygon perspective. We have 4 sides, which I have split into 4 triangles. 1, 2, 3, and then this 4th one. And then by drawing in the apothem, I have the height of this one triangle. There's the length S again, only it's not the same S as we had over here. It's a different S. We know, again, one triangle is 1/2 base S times height A multiplied by 4. And to finish our pattern, let's now look at a regular pentagon. 5 sides, 5 triangles. Each triangle is 1/2 SA, and then again we multiply by 5. And let's take a look at what's going on here. Every time I add a new side, this multiplier goes up by 1. 3 sides, 3 triangles times 3. 4 sides, 4 triangles times 4. 5 sides, 5 triangles times 5. If we had 6 sides, 6 triangles, we'd multiply times 6. And also notice that every time we have this 1/2 SA, 1/2 SA, 1/2 SA. That has not changed from one situation to the other. We have 1/2 SA times a number. And it's a number that's equal to the number of triangles, which is also equal to the number of sides. So let's put this together and establish a formula that works for any number of sides. So 3 sides, 1/2 SA times 3. 4 sides, 1/2 SA times 4. 5 is 1/2 SA times 5. How about n sides? We now have a triangle with we have a regular polygon with n sides. Let's look at the pattern. N triangles. Area of a regular polygon. We know we're going to have 1/2 SA, since that was common to all of our examples previously, times a number. And that number was equal to the sides equal to the triangles. So if I have n sides, n triangles, I multiply by n. Usually the form this is written in is 1/2 ASN. A is apothem, S is the length of a side, N number of sides. That is how you find the area of a regular polygon. There is another form of this. Notice SN. If I have three sides, let's go back here. If I have three sides, 1, 2, 3, and I know every side is the same. Let's say this side is 7, and this side is 7, and this side is 7. 7 times 3, that SN. S is 7, N is 3. I get 21, which is 7 plus 7 plus 7. Over here, I'll keep S7. Now I have 4 sides. 7 times 4 is 28, which is 7 plus 7 plus 7 plus 7. Every time we get the perimeter. SN is the perimeter of the polygon. So another way to write this is to take out the S times N and replace it with P for perimeter. Either one of these formulas will work. If you use 1/2 ASN, well, you're just getting the perimeter from here. If you are given the perimeter, there's no need to find the length of each side. If you have the perimeter, all you need then is the apothem, and then you can find the area. That is how you find the area of a regular polygon. Let's take a look at some examples. We're going to assume that the polygons that are coming up here are all regular. So find area of this regular polygon. We will assume this is regular. Well, we need to determine what A, S, and N are. Now here's A, the apothem. Here's the center going perpendicular to the side. So we assume that that is the apothem. The apothem goes from the center to a side, to the midpoint of a side. And because it's the distance, we have to measure it at a right angle. We're not going to measure distance this way at a non-right angle. So here's our distance. Apothem is 14.4. We need S. Well, here's S, length of a side. And then we need N, the number of sides. So if I start here, 1, 2, 3, 4, 5, 6, 7. We will have our area as soon as we compute this. And it looks like 700.56. Square units. Whatever our unit is, it'll be that unit squared. With regular polygons, you are more likely than not going to have some decimals, and you may also even have some approximations, depending on what information is missing that you need to find. Occasionally, you will have square roots that you have to deal with. So you may need to review that material a little bit. Next example. Speaking of square roots, here we have a regular hexagon. Because this is a regular hexagon, some special rules come into play. So let's see what we need. We have a half. We need A. A is 5 square root of 3. We need S. We have S. We need N. We have N. So we don't really need our special rules. At least not yet. Multiplying this out, we get 150 square root of 3 for our area. And yes, leave that square root as the square root of 3. Unless the problem specifically says to round, do not get rid of that square root. I'm going to do this problem a second time to show you what would happen if we needed to apply some special rules. So I'm going to create a duplicate of this figure. Bring it down here. And I'm going to take something away. I'm going to pretend we did not know what that value is. So this is all we're given. Same problem. Find a area of regular hexagon. We still need ASN, but now we don't know what S is. We still know N is 6, but we don't know what S is based on what this picture gives us. Here's where our special rules come into play. This is a hexagon. It's a regular hexagon. So I know that each of these 6 angles is equal. I also know that when I do this, I cut this angle in half. This part is equal to this part. When I draw on the radius, I get 2 equal halves here. So now the question is, how do we find this? Because I need this in order to find the whole thing. This side right here is equal to this piece right here, and the whole thing together is our S. So I need to know what's going on. Well, because this is a hexagon, I can find the total number of degrees. Hexagon has 720 degrees total. I can divide that by 6 to find what each individual angle equals. Each individual angle is 120, which means when I draw in the radius, 120 gets cut in half, and I have a 60-degree angle. Some more room here. I have a 60-degree angle. I have a 90-degree angle, which makes this a 30-degree angle. So what we have here, here's R, here's 5 square root of 3, here's the 90, is a 30, 60, 90 right triangle. These are the special rules I was referring to a few minutes ago. you may need to go back and review your notes on special right triangles, because without them, you can't go any further. So knowing our 30, 60, 90 rules, 5 square root of 3 is the long leg, which tells me the short leg is 5. I don't need r, I need this value right here. And if that value is 5, that value is 5, and now I know that s is 10, and I can compute the area just like we did before. Now, do you always get a 30, 60, 90 triangle? No. With an equilateral triangle, you will. With an equilateral triangle, the 30 and the 60 will be flipped. With a square, no. You get a 45, 45, 90. With a hexagon, you get a 30, 60, 90, and that's it. All other regular polygons will not be a special right triangle. So what do you do in that case? That's an excellent question, and one that will get answered in this problem. This will be our last example. What do you do? What do you do when you don't get a special right triangle? Well, let's take a look at what we have here. Find area of this. What do we got? Looks like we have 9 sides. We have a regular nonagon. And I'm also given the perimeter. Since I'm given the perimeter, I can shortcut that a little bit. AP. I don't know A though. I don't know the apothem. But I know the perimeter is 108. I know the perimeter is 108. I need to know what the apothem is. So I will draw in the center. I will draw in a radius. And then I will draw in the apothem. So there's my right triangle. Now we have a little work ahead of us. Here's that same triangle. Here's R. Here's A. And I don't know what this side is here. That's what we're trying to find down here. So, because I have a nonagon, I need to know the total number of degrees inside this. That comes out to be 1,260 degrees. Dividing that by 9 angles, each angle is 140 degrees. Drawing the radius, cuts 140 in half, making this a 70-degree angle. So I don't have a 30, 60, 90. I don't have a 45, 45, 90. I have a 20, 70, 90, which has no special rules. So there's only one option left. Because the perimeter is 108, and I know it's a regular polygon, I can divide to find out that each side is 12. If I have 9 sides, they all add up to 108 and they're all equal, each one has to be 12, which tells me that this is 6. Again, I don't care about R. I care about A. I need A to fill this spot. So now we go back to trigonometry to figure out A. I can take this 70-degree angle and observe that this is the opposite side. This is the adjacent side. And that is a tangent ratio. So now we're back in our trig unit, which again, if you need to review that, I would get into your notebook, pull up those notes. And we're going to end up with approximately, let's not use the entire list of decimals here that pop up on the calculator. Let's round this a little reasonably. Let's say 0.48. Use a couple decimals for precision. There's our apothem. There is our apothem. Now that we have our apothem, we can go ahead and multiply this out. And we get an area of, and this is going to be approximately, not equal to anymore. We'll say 9.2. And at the very beginning, I should have put nearest hundredth, because I knew ahead of time we were going to get a decimal. So sometimes you have to use your special right triangle rules. Sometimes you have to use trigonometry. Sometimes you're given everything you need. So here's where previous material is coming back and used to help us solve some area problems. So that is how you find the area of a regular polygon. At this point, you know the drill, and that is all for this section.